So after calculating that initial number of moles, it's just a standard stoichiometry problem. All right, we use the mole ratio, which comes from the balanced chemical equation, always has to be balanced. And then in this question, it was how many grams of silver oxide decomposed. So we use the molar mass there to calculate that number of grams. So how many liters of oxygen at STP are required to form 10.5 grams of water? So what information have we been given? STP, yes. STP, it's almost like a code. It's a secret code for a standard temperature and pressure. So it means our temperature and our pressure are known. And what is standard temperature? 273.15 Kelvin. And the standard pressure? 1 atmosphere. I believe we can treat that 1 atmosphere as exact. It's being defined as 1 atmosphere, so. Okay, so we want to form 10.5 grams of H2O. So that's the other piece of information that we have. 10.5 grams H2O, and we can't really assign that to a specific variable. Maybe pick M, maybe pick something else. And what are we actually being asked to find here? Yeah, the liters of oxygen. So how many liters of O2? So to start this problem, I was trying to figure out how to phrase this, conceptualize it, and generalize it, right? Okay, so pressure and temperature are describing properties of everything in the reaction right now. So everything's going to have that same pressure, everything's going to have that same temperature. So we can't really use that as a starting point to calculate a number of moles of something, right? It's the hydrogen, the oxygen, and the water that's defining all of them, so it's not unique to any of these individual things, and it doesn't really tell us anything about, by themselves, it doesn't tell us anything about the specific quantity of one of the species in the reaction, is the general idea. As a way to explain why we wouldn't start with either of those. The thing that we do have, though, and the thing that we can use to calculate a number of moles of a species in the reaction is the 10.5 grams H2O. Because if we have that, 10.5 grams H2O, we can calculate a molar mass and then use that to figure out how many moles of H2O it is. And in a stoichiometry problem, that's always the first goal. Figure out how to calculate moles of something, one of the species in the reaction. So we got 10.5 grams of water. What's the molar mass of water?
18.015.
We're going to use 18.02. But yeah, it'll depend a little bit on the number of significant figures that you have. For molar masses, so that's equivalent to 1 mole of H2O. And now we want to know how many moles of oxygen there are. So what's the mole ratio?
1 for every 2 water.
Yeah, so we put the 2 moles of water down here, and we're getting that value from the balanced chemical equation. And then 1 mole of what we're looking for, which is the oxygen. So that's our mole ratio, and that'll give us moles of oxygen. And here's where using this sort of railroad track setup doesn't really work with PV equals nRT, because this is really good for converting units. But once we get to PV equals nRT, we're plugging something into a formula to cancel out a whole bunch of units. Yes, you could finagle it to fit in here, but I think it's easier to do it this way. So every time. So 10.5. times 1 times 1 divided by 18.02 divided by 2. 0.29134. Always keep a few extra sig figs.
You said 2 after usually, right? At least.
Yeah, at least 2. So that would be at least 2, right? Yeah, 3 sig figs. So that's moles of oxygen. Oh, I guess we could have fit something in here that does fit into the railroad track thing. So there's 2 ways you can solve it from here. What are those 2 ways?
The ideal gas law.
Ideal gas law, PV equals nRT. What's the other one?
Well, if pressure and temperature are constant, can we use like a simpler?
If they're a specific thing, if we're at STP, we can use the molar volume of any ideal gas, which is 22.4 liters per mole. So we could have put that in here and used that to calculate, but I'll write it over here. So 0.29134 moles of oxygen. I'll do it this way. So it's, yeah, for any gas at STP, it's 22.4 liters per 1 mole. So 22.4 liters over 1 mole and times 2.4. So 6.53 liters of O2. So be on the lookout for that. Again, because STP also tells us the temperature and the pressure, you can plug those into PV nRT equals nRT. You might get, at the thousandth place, some variation, but it's negligible. Cool. Any questions, gas laws? All right. So moving on then.
Actually, sorry.
Yes?
For this particular problem, we didn't even really need the temperature or the pressure at any point to solve it.
Yes.
We needed to know that it was at STP.
Yes.
We didn't need the numbers to solve it.
Yes. Yeah, they're important. You need to know what they are.
Yeah.
And because we're at STP, that means that we don't have to directly plug them into an equation. But if you remember how we calculate this 22.4 liters, it does include the temperature and pressure in it. But yeah, you're correct. So we don't actually have to use those numbers unless you use PV equals nRT. Yeah. All right. So we've talked about kinetic molecular theory. It's a quantitative model that implies PV equals nRT. You can see the textbook for that. The theory predicts the behavior that is consistent with observations and measurements of gases, which is kind of a really cool thing, because if you can describe something in mathematical terms and then do real world experiments and see that your predictions are accurate based on your model, that's a very powerful thing. Because now you can predict a whole bunch of things without ever having to do the experiment first. Once you've got enough verification behind your model. That does, though, this kinetic molecular theory, though, does have certain limits. And we actually talked about what those limits were last time. Where does it start to break down? 2 situations in particular.
It's too cold.
Too cold was one of them.
Pressure's too extreme.
Extremely cold or extremely high pressure. And that's where we start to push those sort of principles of kinetic molecular theory to the limits of being plausible. So one of them being that the particles are infinitely far apart. And once you increase the pressure enough, remember pressure is related to the number of moles. So to increase pressure, you have to add more moles of gas. And as you add more moles of gas, the distance between the particles on average decreases. So we can no longer consider them to be, or assume that they are, infinitely far apart, and therefore not interacting directly. And then when you're cooling down too, things will eventually form solids or liquids. They'll condense. And they won't be moving fast enough that the interactions, the very, very weak interactions, are no longer felt. So we've mentioned this also, that the average kinetic energy of gas molecules depends on the mass and the average velocity. So actually we can flip over to this. So I have that built in here. Where's that page? Here we go. So if I change the mass, right, so you can consider like these particles, the speed that they're moving around, that's representing their energy. I didn't get around to programming their size to scale, but if I take this mass number here, 131, so that's xenon, and let's move it up to, I don't know, radon, 222. It's really similar. All right, well, let's do something insane here. Let's go 500 to exaggerate this effect. There we go. So there we go. Overlapping hotkeys. There we go, 500. So now they're slow, right? But they have the same kinetic energy. Because if I go, is it just doing it if I press 1? Is that what's happening? No. We go back here, right? Kinetic energy equals 1/2 mass times velocity. I keep doing that, volume. Mass times velocity squared. So for these particles, see, it works sometimes. Right, if we increase the mass, now they move slower. So they have the same average kinetic energy at that temperature of 273. There we go. So to maintain the same kinetic energy, average kinetic energy. But it is the average kinetic energy, and so we use a special average of their velocities to represent that. That's this u, I believe it's u and not mu. The root mean squared velocity. So in gas mixture at given temperature, lighter particles travel faster, heavier ones travel slower. So this is the equation for root mean squared velocity. It's a special type of average. It's close to just like your regular average where you take all their velocities and divide by the number of particles, but it's not quite. It's adjusted a little bit. And for our collection of particles, it's proportional to the square root of the temperature in kelvins and inversely proportional to the molar mass of the particles if your molar mass is in kilograms per mole. And that's actually I think I showed you guys this last time too. That is the thing that would pop up if it was behaving. It really doesn't want to do it now. So that is this equation here for the most part, where we've got 8.314, or so 3 times R, which is the 8.314 different units, times the temperature, and then that divided by the mass, and then this is a factor in here just to slow them down because otherwise they go way too fast if you don't divide this by 10. And then the square root of all that. It's probably because the box is too small. I need to make it a bigger box. So using this equation, we can calculate what the sort of average velocity of all of the particles is, just based on the temperature and the molar mass. So I think we did look at this also. Lighter particles have broader distributions. So if you look at the particles of helium or hydrogen, they're lighter, so you have more particles that are moving slower, more particles that are moving faster. They're more spread out over all the possible velocities. Whereas these ones over here for oxygen and nitrogen, which are heavier, you can imagine as you get even heavier, so like the xenon, is going to be even more confined to a narrower range of velocities. Right, so also the relationship between temperature, so as temperature increases, those velocities spread out. So this is for nitrogen. So even if you just take nitrogen, start at 273, and then increase that temperature, you get more and more possible velocities. All right, so if we want to calculate the root mean squared velocity of gaseous xenon atoms at 25 degrees C, a couple things that we have to consider. So, oh, it's not mu. U RMS was the square root of 3 RT over M, and M is in kilograms per mole. So R is a constant. That's 8.314. Oh, also, happy belated Pi Day. Yesterday was Pi Day. Oh, I should have taken a screenshot on my phone at 1:59, because then it would be 3.14159. Next year.
So 26 seconds.
Is that the next two? Yeah. So in 3 years. Oh, kind of. Never mind. So temperature here has to be in Kelvin. Because what is R? R is joules per mole Kelvin. Joules per mole Kelvin. Temperature is going to be 298.15. And then the molar mass of xenon in kilograms per mole is going to be 0.13129. And that's kilograms per mole. That's Kelvin. And we can actually take, this is another place where unit analysis actually works, and you don't even need the equation necessarily. So if we take our 3 times 8.314 and then convert the joules to kilograms meters squared per second squared. So it's kilograms meters squared per second squared times the temperature, 298. Oh, I forgot these units. 0.314. Wait, no, I didn't. I forgot the rest of. Hold up. Kilograms per meter squared per mole Kelvin. This is Kelvin. This whole thing divided by 0.13129 kilograms per mole. And then the square root of all of that, which is a lot when you include all of the units. But you can go through these and the Kelvin will cancel out, moles will cancel out, and kilograms will cancel out. So if we get 3 times 8.314 times 298.15 divided by 0.13129. Then this is 56,451. 0.48. And that's going to be meters squared per second squared. So the square root of that will give us meters per second. So it's 237.59. I guess we really only have 2 sig figs here. Yeah, so it's got to be 2.4 times 10 to the 2 meters per second. So you can see why I have to modify this even. So if I do in this other model, because I'm not even using kilograms per mole here. This is grams per mole. If I divide this by 1,000, they still go way too fast to make any sense. Oh, dang it. There, you can't even see them. Right, so we can calculate the speed of these particles, and that's, yeah, meters per second. How fast is 240 meters per second? That's about 536 miles per hour. Yeah. It keeps, I don't know. It doesn't like me. 540. 530 something. Which, yeah. Cruising speed of 737 is, or maximum speed of a 737 is 544 miles per hour. See, why did it switch to that? I didn't press the button to do that. So our Xenon here is going just as fast as a 737. They are moving, but they're tiny.
And that's slow.
So every single one of them, yeah.
Because that's a big.
And that's slow because it's really big, right? So do this calculation for hydrogen, and they're zooming, but they have the same energy.
Jeepers.
Do it right now. Let us know what it is. All right, so which sample of an ideal gas has the greatest pressure? Assume the mass of each particle is proportional to its size, so bigger equals heavier. And all the gas samples are at the same temperature. What was it?
If I get like a value like 2,713 meters per second, I converted it to kilograms.
Yeah.
101.
Wait, what was it? 2,000?
Wait, we can convert joules to meters per second, right? Or is it meters per second? Meters squared per second. Meters squared per second.
Yeah. But you just have to do.
I kept it as joules. The 8.314 joules per.
Yeah, you can just plug it in as 8.314. I just replaced the units of joules with the kilograms meters squared per second squared.
Because that way you can cancel.
They're equivalent. And yeah, and then you can see that all the units cancel out. So 3 times 8.314, 298.15, divided by 0.00202. Huh. Oh, right. Because that's the average speed. So there's particles that are going faster than that, particles that are going slower. Because the escape velocity for Earth is about 11,000 meters per second. That's how fast you have to be going to leave Earth's gravity well, but huge distribution. All right, sorry, getting too distracted. So which of these would have the greatest pressure? They're all at the same temperature. If the particles are bigger, they're heavier. So that's 7 particles. This one's 7 as well. This one's more than 7. $11 particles. So it's the same temperature. So what do you know about all the particles at the same temperature? They have the same root mean squared speed. Oh, no, sorry. They don't have the same root mean squared velocity. They have the same kinetic energy. They'll have different velocities depending on their molar masses. So the more massive it gets, the slower it's going, but it's the same kinetic energy. So yeah, so between A and B, we have the same number of particles, and that's the only thing that's going to change the pressure. Because the larger particles are there, yes, but they're also moving slower so that they have the same energy. They're bigger, but moving slower, yeah. So C is the highest pressure. Okay. So one of our other principles for this, for kinetic molecular theory, is that our gases, particles are moving in straight lines. We actually think of this property called the mean free path. So how far in a straight line does any particle travel before it hits another particle or hits a wall? And that's the average, yeah, so mean free path. The mean free path for anything decreases as the pressure increases. And that makes sense, right? Because if we have more particles, there's more things that they can run into. And eventually I'll figure out how to calculate mean free path on this, but. Right, so we can look at this. And let me bring this back down to 131. So we got our particles. Looking at the average path, so there's 20 particles in there right now. If I bump this up to, I don't know, 100, right? Just try tracking any given particle. Okay, there we go. Try tracking any given particle, and especially since the box is so small here compared to the number of particles, they're almost constantly running into things. And it's taking them a long time to travel or I guess they're not traveling any significant distance without running into something. And because we have more particles, what does this do to the pressure? Increases, right? So we add more particles, we increase the pressure, mean free path goes down. Can't travel very far before running into something. So then if I cut this back down to, say, 10 particles, right? Now they can actually go a while before hitting the walls or hitting another particle. Okay. So that's a mean free path. And then the whole reason that I made this simulation was, well, partially to talk about these other things, but also to talk about diffusion and diffusion. So diffusion is a process by which gas molecules spread out from a high concentration to a low concentration. So in the model, I don't have a way to do it, we could start them all in the same corner, and then the rate at which they spread out across the space is the diffusion. The process by which they escape through a small hole, which was the whole point of the model, is called effusion. So how fast do the particles make it through that hole and then into the other side or into a vacuum is essentially what we're assuming. So diffusion and effusion are both related to the root mean squared velocity because, right, if the particles are larger, if they're more, I should say, not say larger, if they're heavier, they're moving slower, so it's going to take them longer to diffuse into a space, and it's going to be longer before they happen to, by random chance, pass through the hole in the box. And that's the thing I need to work on next for the model.
Is that similar, like when you have the, I forgot what kind of gas it was, but it was brown and it was staying in the beaker, like it wouldn't get out of it?
Oh, that has to do more with the density. Yeah, from the nitric acid, the copper cycle lab. Yeah, that's density.
I don't really understand diffusion.
So this actually, this is effusion. So if I restart this, all the particles start on the same side, and then we could time, I guess, how long it takes a certain number of particles to get to the other side. And then again, because the sizes are not maybe proportional, right? So it's like takes a while for this to happen, but if I, again, bump up the mass here and just ignore the, not 4,000. Every time. So if I increase the mass, they move slower. So it takes longer for any of the particles to randomly bounce through the hole. So that's why, or that's the relationship here. And that's also why we can, for two different gases, we can determine the rate of effusion relative to each other. So the rate at which they effuse or pass through this hole is going to be the square root of the ratio of their molar mass. So we could take the molar mass of helium, let's see, helium, which would be 4. Let me do it this way, the larger one on top. So we have 4.00, that's helium on the bottom. And then put nitrogen N2 on the top, which is going to be 28.02. So the square root of that. So the rate of the effusion for nitrogen is going to be 2.65. Oh, is that really what the next slide is? No, it's something else. Okay. So that's the, it's going to be 2.645 times slower than helium is. Oh no, it's inverse. That makes more sense actually. So mass of A, rate of A. So helium will effuse 2.65 times faster. All right, so the rate of helium's diffusion is much faster because the particles are just moving way faster.
So it doesn't depend on the amount of moles, it just depends on the mass, whichever.
It's assuming that you start with the, I mean, okay, so the number of moles is going to determine your overall rate of diffusion, but for the same number of moles in a box, no, it might just be.
I think the same number of moles makes sense, because if you have like 3 particles of helium, then you have like, Avogadro's number.
Well, because it's just a ratio.
Yeah.
So if you just,
Well, this is just a ratio, yeah.
Maybe like 1 to 1.
So the numbers, as long as the amounts are the same, that rate for that amount would be the same. But it is also just the ball's bouncing randomly around the box, and so the likelihood of them hitting the hole and going through, getting a little into the weeds. But yes, this would be for the same amounts starting in the same box. Everything else being equal, just replacing helium for nitrogen. Yeah. So if we want to find the ratio of the effusion rate of hydrogen gas to that of krypton gas, so the rate of A over the rate of B equals the square root of the mass of B over the mass of A. This flips because if you want to calculate the root mean squared, it's inversely proportional to the mass. So that would put them both in the denominator. So the rate of krypton is 80, or the mass of krypton is going to be 83.80 over hydrogen, 2.02, and the square root of that. So square root. So it's 6.44 equals the rate of H2 over the rate of krypton. So we would say that hydrogen effuses 6.44 times faster than krypton. Or they have an effusion ratio of 6.44 to 1. Okay, so let's talk about real gases. Ideal gases are great and everything, and for many, many things, you can calculate stuff based on those ideal gases and get close enough to the ballpark. But even if we take these gases at STP, they have slight deviations in their molar volume. So they act much like them, but our ideal gas would be 22.41, but chlorine is 22.06, carbon dioxide is 22.31, ammonia 22.4, helium is ideal.
Just like
So as we talked about before, at high temps, high pressure or low temperature, that's when things start to really deviate from these ideal gases.
Because I'm not ideal gas. I got attraction.
So at low pressures, the molar volume of argon is nearly identical to that of an ideal gas. But as you increase the pressure, the molar volume of argon becomes greater than that of an ideal gas, because at high pressures, the argon atoms themselves occupy a significant portion of the space inside. So then that makes the actual volume greater than that would be predicted by the ideal gas law, because the ideal gas law is ignoring all of the space that the particles take up. And I guess we can throw this thing in here again. Right, like here we could pretty much ignore the space that each of these dots takes up. But again, if I jump this up to 100, now they're taking up pretty significant proportion. Just to see how much it breaks, let's do 1,000.
almost loaded.
It's loading. It does have to constantly track and update each position of the particle, so it's probably not going to do 1,000. Oh. Okay, bye. It's not going to work. All right, so 1,000 particles broke it. I think it might take up more than the volume inside that box. All right, well, we'll come back if it fixes itself. Right, so yeah, when we increase this pressure, now, we're deviating from ideal gas law. These things that we assume for ideal gases no longer are true, or no longer reasonable assumptions. These are kind of insane pressures, though. So we're getting up to like 400, 600, 800 atmospheres of pressure. And the deviations here aren't that huge from ideal gas molar volume. And so we can actually model this, or we can include it in our equations. So Johannes van der Waals modified the ideal gas equation to fit the behavior of real gases at high pressure by accounting for that molecular volume. So if you can include the molecular volume, then you can more accurately predict what the volume of a non-ideal gas is going to be. So this n times B, so B is the van der Waals constant, and it's going to be different for every gas because their molecules are different sizes. I believe the number of moles. All right, so depending on the number of moles of a gas, you have to multiply that by the volume that they occupy. So the other thing that we have to account for is that we're also assuming that there aren't any intermolecular attractions between our particles. And so that's why at high temperatures, the pressure of the gases is nearly identical to that of an ideal gas, because as they're whizzing around this box, even if they have close passes, the force of the interaction is nothing compared to their momentum carrying them past each other. But at low pressures or low temperatures, the pressure of the gas is less than that of an ideal gas, because at lower temperatures, the collisions occur with less kinetic energy, and the weak attractions can affect the collisions, making the actual pressure less than that predicted by the ideal gas law, because you get more collisions between the particles themselves, getting pulled into each other. having a hard time getting away from each other. So van der Waals also took this into account. He modified the ideal gas equation to account for these intermolecular attractions. So A is another van der Waals constant, which is different for every gas, again, because each gas is going to have different attractive forces. So the pressure, the expected pressure of the gas here is deviating, right, as we decrease the temperature, deviates more and more. If you're up over 1,000 for xenon, up over 1,000 degrees, or 1,000 Kelvin, I should say, then pretty much ideal. But even here, right, 273 Kelvin, so somewhere in here, that would be a regular temperature is going to deviate by, how much is that? Let's say it's like there. So 1 or 2 atmospheres even. Pretty large deviation for xenon. So we make this modification to calculations of pressure at low temperatures. So then the van der Waals equation combines both of these. So the pressure of a gas times this modifier constant, or times this modifier, times the volume of a gas minus this modifier. Right, correction for particle volume and correction for intermolecular forces, and still equals nRT. And now for any of these gases, we can calculate what its actual volume would be, or its actual pressure, or the actual number of moles even. All right, do everything more accurately. I guess we're just going to finish earlier today. So a plot of pressure PV over RT versus pressure for 1 mole of gas gives us the deviations, real gases deviate from ideal gas behavior. So for certain gases, we're going to have different deviations. Curves that are higher mean that the most important factor is the molecular volume. So curves that are lower is going to be intermolecular forces. And if you remember stuff about intermolecular forces from Chem 20 or high school chem, makes sense that water would be really low. So it's mostly intermolecular forces that are making the difference there, because water has hydrogen bonding. Whereas all of these, all of the noble gases only have what kind of intermolecular force? It's the same dude. Same name. Van der Waals forces, or London dispersion forces. Yeah, so they're going to have very weak intermolecular forces as it is. And if we had talked about it already, it would also make sense that xenon is the only one of these that has appreciably more deviation because of those intermolecular forces at low temperatures. Does anybody know why that would be? So if we're high up here, like if these curves are above 1, that means it's mostly the space that they take up. If it's below this, that means it's mostly the intermolecular forces that are causing deviation. So why would xenon have more deviation due to intermolecular forces than the other noble gases? Because they're heavier? It is a trend on the periodic table. Because what? They're all noble gases. But xenon's the only one that dips way below. They're all pretty neutral electronegativity. I know we haven't talked about it yet. But what determines the strength of van der Waals forces? Size helps because the electron cloud is bigger. So if you move down the periodic table, the electron cloud around it gets larger and larger and larger. And those electron clouds are almost, you can think of them as squishy almost. And so for every layer of electron cloud you add, you're adding more squish in its electrons. And so when a xenon bumps up to another xenon, its electrons repel the other xenon's electrons, and that creates instantaneous dipoles. And because xenon's so big and its cloud is so big, it can have a stronger dipole moment in those bumping togethers than krypton, argon, neon, or helium. We'll come back to that. Talk about it more. All right, well, I didn't expect to get done this early.